Okay, I'm making this video not in front of the class because I had problems with the laptop in class. But the good news is I think I might have figured out what was causing all my trouble, and hopefully I won't have these kinds of issues again, but we'll see. I still think it probably gets too hot sometimes, and that might cause the pen to blur. But I was having other problems, and those I think I fixed. So today we do radical expressions. When you talk about radical functions, generally that means you have to deal with expressions, equations, and the actual functions. And we did the actual functions in the last lesson. That was all about how to graph square roots and cube roots. Today we deal with expressions. And with expressions, what we're looking to do is to simplify, which could include adding and subtracting, multiplying and dividing, expressions that have radicals in them, not necessarily square roots or cube roots, but most of the time. So this chart is telling us that when you take an even root, so we know about this notation here. Let me make it bigger here. But when you have a radical, right, we know that there is an index which tells you whether it's a square root, cubed root, fourth root, or whatever. There's a radicand, which is whatever is underneath the radical. So this is telling us that when the index is even, square root, fourth root, sixth root, etc., first, we cannot take the square root of a negative number. That's what that's saying right there. If a is less than 0, it has no real nth roots. If a is greater than 0, then it will have 2 nth roots, plus and minus. So, for example, if I take the square root of 4, I get plus or minus 2. If I take the fourth root of 81, I get plus or minus 3. Right, so even roots can't take the even root of a negative number, and the even root of a positive could be plus or minus. Okay, if you have an odd index, then in fact there's nothing undefined. There's nothing undefined, right? You get what you get. If the a is less than 0, for example, if I had the cubed root of negative 8, I get negative 2, no problem. Cube root of a positive number is a positive number. So less issues involved when you're taking an odd root. So the first kind of problems we'll do are to find the real roots of a. And it's given to us with just specifying the n and the a. So if it says find if the n is 3 and the a is negative 216, then I can write that as a radical like 3 negative 216. And let's see. You may not be familiar with your perfect cubes. And if you're not, it might be worth it to sit down and, as I was saying, it might be worth it to make a table of the perfect cubes until you're more familiar with them. I mean, 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, 5 to the third is 125, 6 to the third is 216. It pays to know these numbers. So when I see this cubed root of negative 216, the number's familiar. The only thing that's a little different about it is because it's a negative, that means my answer will be negative. Okay, and here I have the fourth root of 81. So since it's an even root, I have to remember to put plus or minus. So we know, most of us, we don't know the fourth powers of 4 beyond the first few. but just because how fast the fourth powers grow, you really can't do much more than the first few. 2 to the fourth is 16, and 3 to the fourth is 81, and 4 to the fourth is 256. The numbers get so big so quick that they're probably always going to be using the same small numbers. The fourth root of 81 is 3, but because it's an even root, and we've been told to include the negative, we include the negative. Okay. So this is your you try. Hit pause if you're watching this at home. And when you're done, hit play. And I'm going to be going through it already. Okay. The fourth root of 625 is plus or minus 5. The third root of negative 64 is negative 4. The sixth root of 64 is plus or minus 2. And the fifth root of 243 is 3. Okay, next. So we should be able to evaluate roots, which also means rational exponents of numbers. And if they're all these same tried and true squares, cubes, fourth powers of pretty low numbers, we could do it in our head, or we could convert it to a radical, and maybe it'll make it easier. We know, because we did this in the homework from last night, that 16 to the 3 halves means the square root of 16 to the third. 16, the square root of 16 is 4, and 4 to the third is 64. Now, if you need to do it, you do that. I tell you that the further you go in this stuff, you would just look at that 16 and say, because the denominator is 2, take the square root, 4. And because the numerator is 3, cube it, 4 cubed, 64. Okay, now this one is a little different just because it has the minus, the negative exponent. What do we do to simplify the negative exponent part? We flip it. Right, it's negative exponent in the numerator, it's a positive exponent in the denominator. And again, you could turn it into a radical, or you can just say the fifth root of 32. So what number times itself 5 times equals 32? And the answer is 2. And 2 to the third is 8. So you don't necessarily have to turn it into a radical, but if it helps, you could definitely turn it into a radical. And I did it without putting it 1 over, but it's 1 over. So let's evaluate these. These are your U-tries. So go ahead and turn off the video and turn it back on when you're done. Right, the square root of 4 is 2 to the 5th equals 32. Okay, this is 1 over 9 to the 1/2. And 9 to the 1/2 is the square root of 9. The fourth root of 81 is 3, and 3 to the third is 27. Keep doing that. And 1 to any power is 1. Okay. Now these are the properties of rational exponents, and they are the same as the properties, except one, They're the same as the properties of exponents that we dealt with before. The only thing that's different are these examples on the right. You know, when you multiply a to the m times a to the n, you add the exponents, and so on and so on. You can go down and look at them on your own and look at their examples on the right. There is one property that we studied before which is not on that list. And if you think about it for a second, it makes sense. We had one more property of exponents, was that anything raised to the 0 power equals 1. But of course that wouldn't be a property of rational exponents, because we can't really write 0 as a fraction meaningfully. So that one is not in the list, but all the rest are in the list. So we can do some of these. These are going to be you tries. See if you can apply the properties of exponents. I will do the same after you hit pause. So remember, the one property is to distribute when you've got a power outside of parentheses. Distribute 5 to the 1/3 to the 3rd, 7 to the 1/4 to the 3rd. Right, when you raise a power to a power, you multiply, so that's 5 to the 1, and this is 7 to the 3/4. And 5 to the 1 is just 5. Right, 2 to the 3/4 times 2 to the 1/2, that would be 2 to the 3/4 plus 1/2, which is 2 to the 3/4 plus 2/4, which is 2 to the 5/4. So if your exponents are fractions and you're adding the exponents, you need to find a common denominator. So all that stuff about fractions is going to come into play. Okay, 3 divided by 3 to the 1/4, that 3 in the numerator is raised to the first power. The property of exponents says that when you divide, you subtract the exponents. So this is 3 to the 1 minus 1/4, which is 3 to the 3/4. And now this last, I could distribute it. I'm going to get 20 to the 1/2, to the 3/2, sorry, divided by 5 to the 3/2. That's a very messy 5. Which is fine. Okay. Now, this is like the reverse of distributing a power to everything inside the parentheses. We actually have a power, 3/2, which is distributed onto the numerator and denominator. So we can kind of go backwards on this. Why don't we make this 20 over 5 to the 3/2? And 20 over 5 is 4. So it's 4 to the 3/2. Again, use the denominator first. The square root of 4 is 2. 2 to the 3rd equals 8. So these are properties of radicals. Product property and quotient property, as you would think, are relating to multiplication and division, respectively. And we can use these in both directions. You can take a radical, one radical, and split it up into the radical of the factors, or you can take the product of radicals and put them together by combining everything underneath the radicals. Or you could take the radical of a quotient and make it the quotient of radicals. Just split it up. And we might go both directions on that. Remember, this b does not equal 0 is because we don't want to divide by 0. That's a domain statement. We should be that familiar with domains now. So using the properties of radicals to simplify the expressions, I've just copied their examples here today because they're fine, and makes it cleaner for you. My writing wouldn't have added much to this anyways. You can see what they've done in the first problem. It's a product property. We have the product of radicals, so we're making it the radical of a product. Now, the cubed root of 12 and the cubed root of 18, that I could not have simplified. I could not have simplified either one of those. But when I multiply together 12 times 18, I get 216. And I can simplify the cubed root of 216. That's 6. So when it serves our purpose, we might multiply radicals. And here we've got the quotient of radicals, so we'll use the quotient property and make that one radical of the quotient. 80 divided by 5 is 16. So the fourth root of 16 is 2. Okay. And I will note at this point that despite what they said at the beginning about when we take even roots, we're going to use plus or minus, that is true when you're solving an equation, but it's not true when you're given a radical. You assume that they mean the positive, and I can see that they've done that on these problems. I might have missed something that they said in the middle of there, but you might ask yourself the question, why is that not plus or minus 2? And the answer is because we assume they mean the positive, what we call the principal square root. So here's your U tries. Hit pause, and when you're done, hit play. So the product of radicals equals the radical of the product. And 3 times 27 is 81. So this is 3. The quotient of radicals equals 1 radical of the quotient. And since that simplifies, that's cubed root, this is the cubed root of 125, which is 5. Okay, now we're going to start getting into the problems where you really have to use product property, which is when you have the cubed root or the root, the nth root of something which does not completely simplify. So you have to write it in the simplest form. Simplify what you can, and then what you can't, you can't. Like I said, we went through the perfect cubes before, and they included 1, 8, 27, 64, 125, 216. And you could see that 135 is not in that list, right? It goes from 125 to 216. So the way you simplify, you say, okay, is 135 a perfect cube? No. Does it have any factors that are? Okay, you can check against your list of perfect cubes. Just keep dividing 135 by all the factors in this list that are less than 135. Now, there are good reasons why you really don't need to divide by 125, but just so we've got a rule, just start with 125 because 125 is less than 135. And if it divides in evenly, then you know you found the factor. But it doesn't. So you divide 135 by 64. It doesn't divide evenly either, right? You get a decimal. Then you try 27. And it turns out that 135 divided by 27 is 5. So we can split this radical. We're going to use the product property in the opposite direction now. We're going to take a radical and make it the radical of a product, and then make it the product of radicals. And this cubed root of 27, that part we can simplify, and so we do. So we've made it more simple. We can't completely simplify the radical, but we can make it simpler than it was. Now, adding and subtracting radicals, in order to add or subtract radicals, they have to be what we call like radicals. Just like when we add or subtract polynomial terms, they have to be like terms. Well, it's the same thing with radicals. And we add them the same way as we add like terms. We add like radicals by adding or subtracting the coefficients. So in order to be like radicals, they have to have the same index, we know that word, and the same radicand, we know that word. So the fourth root of 10 and the fourth root of 10, these two are clearly like radicals. So you can add them up, and you add them up by adding their coefficients. 1 plus 7 times the fourth root of 10, which is 8 times the fourth root of 10. We know we can add, or we can represent a radical with rational exponent notation. So this 8 to the 1/5 and 8 to the 1/5, that's like saying this is the same radicand because of the 8s, and it's the same index because of the 5. And so you can add those up by adding the coefficients. 2 plus 10 is 12. So if you have like radicals, add them up by adding the coefficients. If you don't have like radicals, then you can't add them up. Okay, when you look at this problem here, you might look at it and say, well, those aren't like radicals. I can't do anything. But actually, the cube root of 54 is not in its simplest term. And until you've tried to simplify it, you can't really say whether they're like radicals or not. So the cube root of 54. Okay, I could go back to our list, but I'm just going to speak knowledgeably that I know 54 is not a perfect cube, but it has a factor which is a perfect cube, and that is 27. 54 is 27 times 2. So we're using a quotient property to make a product of quotients. 27, the cube root of 27 times the cube root of 2. And we can simplify this cube root of 27. That's 3. So now these are like radicals. All right, they're both cube roots, and the radicands are 2. So go ahead and subtract them by subtracting the coefficients. That's a 3 minus a 1, which is 2. So if you have two radicals that are not like radicals, make sure that they can't be simplified into like radicals. So this is your chance to do a U-try. Hit pause, and when you're done, hit play. So clearly we can't simplify the cube root of 5, but we might be able to simplify the cube root of 40. Okay, 40 is not a perfect cube, but does it have any factors that are perfect cubes? Well, let's see. There's 1 times 40, there's 2 times 20, there's 4 times 10, and there's 5 times 8. Do you see any cubes there? Yes. There's an 8. So let's split this up into the cubed root of 8 times the cubed root of 5. The cubed root of 8 is 2. So I've got 2 times the cubed root of 5 plus the cubed root of 5. Right? How many cubed roots of 5 is that? Well, it's 1 plus 2. So that's 3 times the cubed root of 5. Okay, now we get into simplifying radical expressions that include variables. And this is where we get into when we take the even root, we assume they mean the positive. Right? So here's our nth root of x to the n. It's like saying the square root of 5 squared is 5. Of course, the square and the square root, they cancel each other out. The third root of 3 to the third is 3. Right? The cube root and the cube, they cancel each other out. Well, that's what this is saying here. But because if the n is even, if the index is even, we know that you could actually get plus or minus. The square root of 4 is plus or minus 2. But for our purposes here, we're taking the absolute value. And that means we only want the positive. So the absolute value symbols will not be necessary if we can assume that all the variables are positive. and most of the time that will be given. In the homework problems, it's absolutely given. Okay, this becomes a little different when we solve equations. Then we can't just say we want the positive. Or actually, we can, but we'll see how that works. That'll be the next lesson. So here's an example of simplifying a radical which has a variable expression inside of it. It's kind of funny that every one of their examples, it seems like, is cubed roots, almost no square roots, which is good because we're going to do fine with the square roots, much better. So more practice with the cube roots is probably a good idea. So, you can see what they're doing here. They're using that property which says that if you take the radical with an index which matches the power that's inside, then you can take out whatever it is that's inside, right? The cubed root of 4 to the third is going to be 4. The cubed root of y squared to the third will be y squared because the 3's are matching up. Now that's not the way I would normally do it, but there's nothing wrong with it. They're equivalent. Everything's equivalent, right? The cubed root of 64, without writing that as 4 to the third, I know that that's 4. And the way I figure out how many of the variables come out is I divide. Take the exponent of 6 and divide by 3. 6 divided by 3 is 2. That means 2 y's come out. 4y squared. Okay, so you try the same on the one below. Hit pause, and when you're done, hit play. So the cubed root of 27 is 3. And how many q's will come out of this? It's the cubed root of q to the 9th. So that's 9 divided by 3 is 3. So that's q to the third. Okay, division. So in this problem, you can see that we are taking a root where the index is actually divides evenly into the exponents. So that means everything's going to come outside of the radicals. You could see how they do it again. They don't have to do anything to the m to the 4th, but they take n to the 8th and they make it n squared to the 4th. Now they've got the index matching the exponent, so they pull out the n squared. Now personally, personally, I wouldn't do that. I would just take this, say 8 divided by 4 is 2. So in the numerator, I've got 4 divided by 4 is 1. In the denominator, I've got 8 divided by 4 is 2, so n squared. So go ahead and try that on the denominator. Hit pause, and when you're done, hit play. And this will be 10 divided by 5 is x squared. 5 divided by 5 is y. Okay, next. So again, here's where we're going to simplify what looks like a pretty complicated radical, and not everything is going to come out of the radical. And you can see what they do. It's not necessarily the way I would do it, but it's like always. It's essentially the same thing. Because I'm doing this thing of dividing the exponent by the index. What I do has a little more to do with that. So I would take this, and you can follow their work, and you'll be able to see how their work and my work is pretty much the same. I'm going to take the 5th root of 4a to the 8th, b to the 14th, c to the 5th. And now let's one by one, let's look at all these factors underneath the radical. Can 4 be written as the 5th power of anything? The answer is no. Nothing I can do to simplify that, so let me just write 4. Okay, a to the 8th, I hope we can see that as an 8. I don't want to mess that up. A to the 8th, see, 8 divided by 5, the index, doesn't go evenly. So I'm not going to be able to take out all the a's. Okay, well, let's think. What's the most a's that I could take out? Which is like saying, what's the greatest multiple of 5, the index, that's less than 8? And the answer is 5. So let's take this a to the 8th and let's make it a to the 5th and a to the 3rd. Right? We know by properties of exponents that's the same thing. 5 plus 3 is 8. Okay, b to the 14th. 14 divided by 5 doesn't go evenly. What's the greatest multiple of 5 less than 14? The answer is 10. So this will be b to the 10th, b to the 4th. Okay, now c. c to the 5th, the 5th root of c to the 5th, actually that's going to go. So I don't need to split that up. So I've broken up everything that needs to be broken up. Now I'm going to come along here and I'm going to take the radical of all these individual factors. Right? That was a 5, 5, 5, 5, 5, and 5. The 5th root of 4 can't be simplified. The 5th root of a to the 5th. Now that can be simplified. That's a. The 5th root of a to the 3rd can't be simplified. The 5th root of b to the 10th. 10 divided by 5 is 2. So I got that one. b squared. The 5th root of b to the 4th. And then finally, the 5th root of c to the 5th, which is just c. So factor by factor, I took all the roots that I could, and now I'm going to combine everything that's outside the radical, which looks like a, b squared, and c. And then combine everything that's inside the radicals. I wrote a 3, and that's a 5. That should have been a 5. And that would be 4, a to the 3rd, b to the 4th. Now if you look and see the way that they split this up here, I mean, they kind of did the same thing. First they split up the a to the 8th into a to the 5th and a to the 3rd. They split up the b to the 10th and b to the 4th. That's all I did here too. Okay. Then they wrote all the things could be simplified in one radical, all the things that couldn't in another, and they did it. It's essentially the same thing. Now, this is an example of dividing where not everything's going to simplify, and it kind of crosses a line of what we would say is a rationalizing the denominator situation, which we don't really have to do in this in Algebra 2. It's not in the standards of learning. But I kind of like the way they've dealt with it here. I've actually not seen this before, so I don't have a problem with doing it this way. Right? The cube root of x and the cube root of y to the 8th, we can see that we're not going to be able to simplify anything like that. Right? But if I multiply numerator and denominator inside the radical by y, now I've got a y to the 9th in the denominator, and 9 divided by 3 is going to simplify. So you can see they split it up now. They had the quotient of the radical of a quotient. Now they've got the quotient of radicals. And the denominator of that can be completely simplified to y to the 3rd. And we are getting close to the end here. Perform the indicated operation. Again, assume all variables are positive, which is almost always the case. Okay, you can see again, we are adding radicals. And in order to add radicals, they have to be like radicals. In this case, we're adding square roots of w. So the index is the same, and the radicand is the same. So we can add them by adding the coefficients. 1/5 plus 3/5 is 4/5. Just looks like such a long string there, but that's all the work. It's actually, we're just adding up these two right there. Now, this is like the problem we did before. They don't look like they're like radicals, but they can be, you can see both of them can be simplified somewhat. I mean, I can see that this z to the fifth under the radical, some of that's going to simplify because the index is less than 5. And we've already dealt with, I think we've already dealt with 54 having a factor which is a perfect cube. So that's what we're going to do. In fact, I think I'm going to, well, I'm going to simplify it because honestly, they've kind of skipped some steps here. You know I can't simplify the 2, but I could split the z to the fifth into z to the third times z squared. And it's going to still have that 12 out in front. So this is cubed root, cubed root, cubed root, which is going to give us 12z times the cubed root of 2z squared. And then this other one, again, we can write that as z, there's a minus in front of that, times the cubed root of 27 times the cubed root of 2 and the cubed root of z squared. So that's going to give us 3z times the cubed root of 2z squared. So by doing that, now we do have like radicals. Right? They're both cubed roots, and 2z squared is the same radicand. Now, how do you simplify this subtraction? You say 12z minus 3z, which is 9z. So you go ahead and try this one underneath, 13. Pause and hit play when you're done. So this I could split up. This is the square root of 9, the square root of w to the fourth, and the square root of w. Minus w times the square root of w squared times the square root of w. This is 3w squared times the square root of w minus, okay, this square root of w squared is going to give me a w. Combined with that w gives me w squared, and I still have square root of w. So we've got 3w squared minus 1w squared times the square root of w, so that is 2w squared times the square root of w. And that's it.